Welcome to the distinguished lecture series of the Indian Mathematics Consortium. The aim here is to host virtual colloquia by some of the best researchers and expositors around the world. The speakers are carefully chosen by the scientific committee from among mathematicians who are not only distinguished researchers, but are also known for the quality of their exposition. The principal aim here is to make the talks as widely accessible as possible, especially to PhD students. With this in view, the format of most of the talks will be in two stages. First, there will be a pre-recorded talk by the speaker, which will be posted online. Interested audience can then view this at their leisure and communicate questions, if any, to the organizers. The second stage will be a live interactive session between the speaker and interested participants, and that will be held about 2 weeks after posting the online talk. The approximate duration of the talk will be about 45 minutes, and that of the interactive session will be about half an hour. The Distinguished Lecture Series is co-hosted by IIT Bombay and ICTS Bangalore. Welcome.
Welcome, everybody. I'm Professor Prahlad Harsha from the School of Technology and Computer Science at the Tata Institute of Fundamental Research, Mumbai. I'm delighted to introduce Professor Irit Dinur, this month's speaker at the TMC Distinguished Lecture Series. I have known Professor Dinur since the early days of my graduate school. From then to today, she has been, in more senses than one, a role model to me and several others, inspiring us over the years. I've been fortunate to have closely collaborated with her over the years. Professor Dinur is a professor of computer science and applied mathematics at the Weizmann Institute of Science, Israel. Professor Dinur is known for her foundational work in theoretical computer science and combinatorics, especially in the areas of probabilistically checkable proofs, also called PCPs, hardness of approximation, and more recently, high-dimensional expanders. In the area of PCPs and hardness of approximation, Professor Dinur is best known for her works on hardness of approximating the minimum vertex cover and an alternative proof of the PCP theorem. The former work was part of her PhD dissertation from Tel Aviv University, Israel, which she did under the guidance of Professor Moli Safra in 2002. In 2006, Professor Dinur gave a dramatically simple and radically new combinatorial construction of probabilistically checkable proofs, leading to an alternate proof of the celebrated PCP theorem, which completely excited the entire TCS community then. For this work, she was awarded the Gödel Prize in 2019. Professor Dinur has also been a plenary speaker at the International Congress of Mathematicians held in Hyderabad. More recently, Professor Dinur has been leading some foundational work on high-dimensional expanders and their connections to theoretical computer science, especially in the context of coding theory, PCPs, and testing. In the lecture today, she will be speaking on some very recent and exciting work on applications of high-dimensional expanders towards construction of locally testable codes.
Okay, hi. I'm going to talk to you today about error-correcting codes with constant rate and distance, and that they have this property called local testability. So these are called locally testable codes. This is very recent work with Evra, Livne, Lubotzky, and Mozes. And let's begin. So let's recall what error-correcting codes are. We are just talking about linear code. So this is a linear subspace of n-bit strings. And every string is depicted here as a point, called a code word. And the idea is that you're sending a message over a noisy channel, some bits can get flipped, and the recipient gets a point that's maybe not where you send, but maybe a little bit removed, and the recipient can search around until it finds the closest code word, and that's going to be the message you actually sent. And that's what the modern theory of error-correcting codes is based on, and we use it all the time in storage on our hard drives, in cell phone communication, and all over the place. Error-correcting codes are used to correct errors. The nice thing is that if you manage to get your code so that every pair of points is far apart, differ on many bits, then this algorithm that the recipient searches for the nearest code word will not allow confusing one code word with another unless too many errors happened. And the parameter that measures this is the distance. It's just the minimum over all pairs of distinct code words of the number of indices on which X is different from Y. Okay, so that's called the distance of the code, and we normalize by the length N. So it's a number between 0 and 1. And the second thing we really care about is how many messages do we encode, right? So the number of points in our subspace is the number of different messages that we can encode. And so log of this number is like the number of information bits we send, whereas N is the number of actual bits we send, and the rate measures the ratio between the two things. So the dimension of the subspace divided by N is the rate of the code, how many information bits per actual bit are being sent. And of course, the golden standard is to get both of these to be as large as possible, but of course they conflict. So the nice thing is that you can get both of them to be constant while the length of the encoding goes to infinity. Okay, now let's move to talk about local testability. So local testability is a much newer parameter, whereas error correcting codes started already in the end of the 1940s by Shannon and Hamming. Local testability is something much newer. And the setup is this. You're looking at a string that's supposedly a code word. And is it in the code? So in local testing, you don't want to read the entire string and make a computation. Instead, you want to very quickly look at just a few bits and make your decision in a randomized way. So you're going to just read a tiny part of your word. And the formal definition is this. Code is locally testable with Q queries if there's a randomized algorithm, we call it a tester, that has query access to the given word W. It reads Q locations from the word, just Q bits or Q symbols, and then it says accept or reject. If the word is in the code, it will be accepted with probability 1, always. If the word is not in the code, well, I would love to say that then it's going to always be rejected. But that doesn't make any sense, right? Because if you have a very long word and it was in the code, but then someone flipped to one single bit, the tester just reads a tiny part of this word. So with very high probability, the tester won't even notice this bit flip. So it's not fair to require the tester to always notice everything. Instead, what's reasonable is to expect that the probability of rejection is proportional to how many bits were flipped to, which is called the distance of W from the code. How many bits do you need to flip to make W actually in the code? Okay, so this is the requirement that we have over here. And Q, the number of bits you're reading from the word, is called the locality of the tester. And such codes are called locally testable codes, or LTCs. Now, I'm going to give another or similar definition of an LTC by looking at two different measures of distance. Okay, so if you have a linear subspace, a code, you can think of a sequence of linear constraints that define the code. So basically, the code is all the strings that satisfy all of these linear constraints, T1, T2, and so on. And I'm going to call them tests. Given a string W, there's two ways I can measure how far W is from the code. The natural way is the Hamming distance. I just measure how many bits do I need to flip until I get to a word in C. The T distance, I invented this for this talk, is a count of how many of the test constraints, how many of these TIs are violated, are not satisfied by W. Okay, what fraction of the tests are unhappy? Now, Hamming distance is the most natural. It doesn't depend on the representation, whereas the TIs, this depends on which TIs you choose. But the Hamming distance might be hard to compute, right? Because if you're given W, there's like an exponential search space until you reach the closest word in C. Whereas the T distance is easy to compute. You just apply each of the TIs on the word and you see. And you can even estimate it randomly by just selecting a few of the TIs and running them. So an alternative definition for an LTC is an error correcting code where the T distance actually gives you a very good estimate for the Hamming distance, meaning that Well, if the t distance is 0, all the constraints are happy, clearly you're in the code. But more interestingly, if the t distance is small, it means that you are close to being in the code. And this property certainly doesn't hold in general for codes, but it holds for locally testable codes. So you can think of this as the definition. And why is this definition interesting? Well, look, it's potentially useful. If you can, you get a word, you don't know whether many errors or few errors happened. You can test and see, did many errors occur or not, by just looking at a few constant locations. If you see that too many errors have happened, it means that the word that you got is far from an actual code word. You can just ask the sender to send you another copy. So this can speed up a lot of communication. Okay, so where did locally testable codes come from? The codes that historically have been studied in coding theory are completely not locally testable. And the idea that you can even expect the code to be locally testable is not necessarily something you would come up with. It really comes from the study of a very important notion in complexity theory called probabilistically checkable proofs. It turns out that NP proofs can be encoded in a way that allows very, very fast checking if you allow randomization. And this has a lot of implications for optimization, for interactive proofs. It's a very well-developed theory by now. And to construct these PCP encodings, you really need implicitly locally testable codes. So I won't go into a lot of the details, but LTCs have begun to be studied as an object of their own. And there were a lot of works trying to get better and better parameters, but until this work, it was believed that, or the only codes that were known had rate that vanishes to 0. And some people, including myself, tried to even prove lower bounds based on the belief that maybe LTCs need some more redundancy in order to make them work. But the recent direction of a high-dimensional expansion seemed very exciting. I'm not going to any details, but high-dimensional expanders are like expander graphs, but they had more layers on them. And they give you some kind of local to global effects that seem related to local testability. And you can see this also in what I present next. So the main result I'm talking about today is the following. For every parameter R, and there exists a parameter delta and Q such that we have an explicit construction of an infinite family of error-correcting codes with rate R, distance delta, and that they're locally testable with Q queries. And in fact, relying on previous reductions, you can make R and delta to be as close as possible to something called the Gilbert-Farshamov bound. And this is the best error-correcting codes that we know meet this bound. So it basically means that you don't pay anything in terms of rate and distance if you want to add the extra property of local testability. And this I find quite surprising. Very recently, a pair of researchers, Pantelev and Kalachev, proved a very similar result and a very, very similar construction, completely independently, as far as I know. They also construct something called the quantum LDPC code, low density parity check code. And I recommend to check out their work. So I'm going to talk about expander codes, which are codes that were already built 25 years ago by Sipser and Spielman. And they serve as the basis conceptually of our codes. Then we're going to move to talk about a two-dimensional object, like a graph, but with one more dimension of squares, based on Cayley graphs. And then we're going to define the code on this graph with squares and look at a couple of properties. So let's go back to the expander codes of Sipser and Spielman from 1996. These are error-correcting codes that are built by taking an infinite family of expander graphs. An expander graph, in our context, will be a D-regular graph. So you think of D as fixed, like 10, and the number of vertices in the graph is growing to infinity. And we say that it's an expander if no matter how you split the vertices into two parts, there's going to be many edges crossing between the parts. So even though every vertex is only connected to a small number of neighbors, when you split the vertices, you're going to see a lot of edges. So we start with a family of expander graphs and one fixed base code on d bits. So it's a constant size object because remember, we think of d as being 10 or some number. And from these two objects, we build a code. And the code is going to be a subspace of the set of functions on the edges of the graph. So you look at all labelings of the edges by bit 0 and 1, and you allow only those labelings so that the local picture, when you look at a vertex and you order the edges in some arbitrary way, the function gives you a string of d bits. You want this string to be in the code C0. So if C0 is a linear code, these are just a bunch of linear constraints. And so the entire code is defined by a collection of linear constraints. It's a linear code. That's the expander code of Sipser and Spielman. And what's nice about this code is that because of the expansion, you can easily prove that it has distance. Because imagine you have two code words that are different from each other. And let's look at a specific vertex that sees some edge that is different. Then this vertex, because the string it sees around it is in the base code C0, it sees two different code words of C0, right? Because C0, if we assume that C0 itself has some constant distance, say delta 0, then delta 0 of the neighbors of this vertex must have differing bits. And so you start with one edge that has some difference and you already see a bunch of edges. But now you move to the neighbors. And again, each neighbor, because he has one non-agreeing edge, it must have many. And this propagates and propagates. That's how you prove distance for these codes. The actual argument, if you know something about expanders, expander mixing lemma, it's a very elegant and very short argument. The second thing you can see about these codes is that they have good rate. How do you prove that? You basically count linear constraints. If your code C0 has sufficient rate above 1/2, then just by counting the number of linear constraints, you will see that this code has positive rate. So there you have it, a code with positive rate and distance. People sometimes also like to look at the so-called Tanner representation of these codes, where you have a bipartite graph with left vertices for all the bits of the code. So here these vertices are going to be one for every edge in the expander graph. And the right vertices are for the constraints of the code. So here we're going to have a right vertex for every vertex in the graph. And the interpretation of this vertex is that it's connected to all of the edges incident on the vertex. And then it imposes a local constraint that says these bits need to belong to C0. So this is the Tanner representation. And one question that's interesting to ask about expander codes is, are they maybe already locally testable? And the answer is that generically, the set of constraints spanned by the expander code are actually full rank. No constraint is linearly dependent on the other constraints. And what this means is that if you remove one constraint, the code doubles in size. And if you take any one of the new code words that were not there before but were added, typically it will be far from the code. And at the same time, it violates only this one extra constraint that was removed. So it's as far as possible from locally testable because the measure that measures the distance is very large, but the measure that measures how many constraints are violated is actually very small. It's one out of all of the constraints. So what we really need is some more linear dependencies between the constraints, and we get that by moving one level up and having a second dimension. So now we're going to have vertices, edges, and squares. These are 4 cycles in the graph. And we're now going to put the bits of the code words not on the edges, but rather on the 4 cycles themselves. And so if previously the bits were on the edges and the constraints were on the vertices, now the bits are going to be on the squares and the constraints are going to be on the edges. And the vertices are going to supply us with an extra level of linear dependency among the constraints. So how is this done? Well, let's start with a finite group G. We think of an infinite sequence of groups that grows to infinity. And we're going to take a set of generators of G that's symmetric. So if A is in the set, A inverse is also in the set. And then the Cayley graph of G with generators A is defined to be the graph whose vertices are the elements of G. And an edge takes you from G to A times G. The symmetry of the generating set means that the graph is not directed. Actually, we're not going to take just one generating set, but actually two of them, A and B. And we're going to look at two different Cayley graphs. One is the blue Cayley graph with generating set A, and we use left multiplication. And the other is the red Cayley graph with generating set B and right multiplication. So here you move from G to GB, and here you move from G to AG. What is the significance of going right and left at the same time? This allows us to get these nice squares, because if I multiply by B from the right and A from the left, you get to the same place as if you multiplied first by A from the left and then by B from the right. So let's see this in more details. So here I have my little square that's formed by these two operations. So fix a specific group element G, so it's a vertex in my graph, and look at two edges, one that's going along an A generator and one that's going along a B generator. You see that what I get here is a square because I can first do AG and then AG times B, or I can do G times B and then A times G times B, and I get to the same place. So A, G, and B give me a square, and the square is rooted because I'm kind of singling out the vertex G. The same square can be viewed from different roots. For example, you can view this square from the root G times B. So here from G times B, you can either go to A times G times B, or you can go to B inverse from the right, so G times B times B inverse, which takes you here. So you get to the same square, but from this different root. And in general, the unrooted square will be the set of the four different rooted squares. And the square will naturally contain the edges as in the picture and the vertices as in the picture. And so let's now define the left-right Cayley complex. You start with a finite group and two symmetric sets of generators, and then you have vertices corresponding to the group elements, edges corresponding to left multiplication and to right multiplication, and the squares are just these sets of rooted squares where you take four rooted squares and you call them a square. So we're going to say that this Cayley complex is a lambda expander if each one of the two underlying Cayley graphs itself is a lambda expander. And it's kind of well known that you can find easily infinite families of bounded degree expander graphs, and this will give you infinite families of bounded degree left-right Cayley complexes that are lambda expanders. Let's look at how the left-right Cayley complex looks like from the inside. Suppose I have an edge from G to AG, and I want to know who are the squares touching it. I can look at the vertex G and look at all the right neighbors, G times B1, G times B2, and so on. And I can look at AG and the same neighbors, AG times B1, AG times B2, and so on. And they match, and of course, each right neighbor forms one square. So all in all, I have this edge from G to AG forming a spine, and the squares are like the pages in a book along this spine. Symmetrically, if I have an edge from G to GB, and I look at all the squares touching this edge, Now I have the left neighbors from G to A1G, A2G, and so on, and the same neighbors on GB to A1GB, A2GB, and so on. So the squares, again, form the pages of a book where the spine now is the edge GGB. And you notice that there's a one-to-one correspondence between the members of A and the squares touching this edge. Previously, we had a one-to-one correspondence between the members of B and the squares touching this edge. Now, before I move to talk about how the neighborhood of a vertex looks like, let me just mention that every edge has all these pages turning on it. But if you look at one square, it belongs to 4 different books, one on each edge, right? So you can turn the pages this way, but you can also turn the pages this way, and so on. How does the complex look like from the point of view of a single vertex? Well, the vertex has A neighbors of the A type and B neighbors of the B type. And for each choice of an A neighbor and a B neighbor, there's a square moving from the A neighbor to the middle guy to the B neighbor and back. Right? So if I look at this A edge, think of it as a spine. I have all the squares corresponding to all the different B neighbors I can choose. And this forms a row in this little matrix. This little A by B matrix really organizes all the squares that touch the vertex G. So if I fix one of the A neighbors and I range over all the B neighbors, I get an entire row. Whereas if I fix one B neighbor and I range over all the A neighbors, I get an entire column. And this column is like a book on the B neighbor, and this row is like a book on the A neighbor. So in general, the squares form an A by B little matrix. And altogether, this maybe explains the picture we had in the beginning of at the first slide, where you have all these squares and you can fold them and move to different squares in any of the 4 directions. Finally, we have reached the code itself. Having defined the Cayley complex, where vertices, edges, and squares, if you also give me some base codes, basically a linear subspace CA of 0, 1 to the A and a linear subspace of 0, 1 to the B, we can together form the new squares code, just like we formed the expander code by taking an expander graph and a base code. Now we're going to take, instead of an expander graph, we're going to take a left-right complex and a base code. So the bits, as we hinted before, are going to be placed now on the squares, as in the picture here. And the constraints are going to be for every edge. Every edge will constrain the bits on the squares surrounding it. And here's the definition of the code. The code is the set of all functions labeling the squares by 0, 1 bits, such that the following constraints hold. For an edge from G to GB, if you look at all the squares touching it, they correspond to the elements of A. So you can view the string of bits as a function as a string in 0, 1 to the A, and you want this string to be in CA. Symmetrically, if you fix an edge from G to AG, and you look at all the squares touching this edge, now you get a string of B bits, and you want this string to be inside CB. That's the definition of the code. Now, if you want, you can try to analyze the rate and the distance, and you'll see that the very, very similar analysis to what we had for the expander codes carries over here, and very easily you will see that the rate is something that has to do with the rate of the base codes CA and CB. If you assume that this rate is R0, a number between 0 and 1, then our rate will be at least this number, which is positive as long as R0 is above 3/4. As for the distance, if you assume that the base code has distance delta 0 and that the Cayley, left-right Cayley complex has expansion lambda, your distance will be positive as long as delta 0 is bigger than lambda. A third property, which is really the new thing here, is that this code is also going to be locally testable as long as some condition holds on the code CACB. And for this, I want to first observe that local views in this code are themselves so-called tensor codes. What is a tensor code? If you have two codes, CA and CB, the tensor code is just a collection of all A by B little matrices such that every column is in CA and every row is in CB. That's the definition of a tensor code. And the claim here is that if you have a function that's in our code, as defined here below, if f is such a function that satisfies these constraints, then for every fixed vertex, if you look at the value of f on all the squares touching this vertex, you will see a tensor code. And this follows directly from inspecting the definition. So our main theorem is that if you start with a left-right Cayley complex, that's a lambda expander, and if some local testability condition holds for CACB, namely, it is what we call row robustly testable, which I'm not going to define, you can look at the paper. And if there is some condition relating lambda, delta 0, the distance of the base code, and rho, the local testability, then the local testability of the local view of the tensor code lifts to local testability of the entire code. And what would be the local tester? Very, very simple. Select a random vertex. Read the entire neighborhood of this vertex, all the A times B squares that touch this vertex. Check that it belongs locally to a tensor code, and accept if so, reject if not. That's the tester. That's the local tester. And what is the main claim? The claim is that the probability that you fail, the fraction of vertices that don't see a local tensor code word, is an upper bound on the distance of this function from the tensor code. So now I want to talk about how to prove local testability. But actually, before we do that, why are the expander codes we discussed earlier, why are they not already locally testable? So we mentioned something, but I want to revisit this question. Remember that in an expander code, the constraints are full rank, so that if you remove a constraint, generically the size of the linear space defined by these constraints will increase in dimension. So the number of code words will double. So this kind of one of the new code words satisfy all of the constraints except for the one that we removed. And yet, since there are many such code words, some of them will be far from the code. So this kind of word will be exactly a problem for local testability because it violates this inequality, whereas on one hand, it only violates a tiny fraction of constraints, 1 in m, but on the other hand, it's very far from the code. In our code, this phenomenon doesn't happen. Let's see. So suppose we take some edge and we remove all the constraints touching this edge. So all the squares around this edge are now, we don't put any of those constraints. Does the code change? So in fact, if you look at one of the vertex endpoints of this edge, this vertex, before we removed the constraints, it saw an A by B little matrix where the local view was supposed to be a tensor code. But in fact, in a tensor code, even if you remove the constraints along an entire column or an entire row, this will not affect the tensor code. It has this kind of robustness because the constraints in a specific row are spanned by constraints in other rows. So if you take a tensor code, you remove all the constraints of row number 13, the code will not change. And in fact, when you look at the code words on this row, they will have to satisfy all the constraints that you thought you removed. And that's because the constraints are not linearly independent. Tensor codes has many linear dependencies among their constraints. So this is a good thing if you're trying to prove local testability. Of course, we need more than that, but it's already a good start and it distinguishes our code from expander codes. Okay, so how do we prove local testability? What we need to show is that for any function from the squares to 0, 1, so it's a potential code word, it's not necessarily a code word, we can always find an f prime in the code such that the fraction of constraints violated by our original function upper bounds the distance of our function from this code word f prime. Of course, there is a multiplicative constant that we pay. So this is our goal. If we are given a function that violates half of the constraints, we don't need to find anything. The zero code word will satisfy this inequality automatically because this is already a constant. So, and the distance is at most 1. By picking this constant to be small enough, we get this inequality. So we have to have in mind the situation where we are given a function f. It violates only a small fraction of the constraints, and our goal is to find some code word that's close to this given function. That's our task. And the way we do it is by an algorithm. The algorithm works as follows. First, for every vertex, you look around at the little neighborhood around the vertex. So you look at all the squares. This is the notation where the root is at G and you vary A and B. So it's basically the little collection of all squares touching your vertex G. And you expect to see there a little tensor code word. But of course, F might be arbitrary. You might see something else. So let T sub G be the closest tensor code word to the F that you see. And if there are ties, choose one arbitrarily, it doesn't matter. So now for every vertex, we have a local view that's okay. But of course, if F had some problems and had some non-accepting local views, then it could be that now the little T sub G's are conflicting. I mean, it might be that all the T sub G's are completely in agreement, and then we've actually found a code word, because now that we have a collection of completely agreeing local views, we can define f prime according to these local views, and we'll be happy actually. And if you think about it, f prime is not very far from f, right? Because f prime is only different from f in the number of locations that corresponds to how many local views weren't perfect for f. So you exactly get that the fraction of bad local views is related to the distance of f prime for f. So that's kind of a baby case. In more generality, the local views can have disagreement, and we're going to measure the number of pairs, number of edges where you have a vertex G and a vertex G prime that have some disagreement. We're going to measure this by phi. And our algorithm will locally try to fix things so that phi decreases until it gets stuck. That's the algorithm. So what does it mean, locally fix things? If you're at a vertex and you can change your local views so that now you agree with more of your neighbors, go ahead. And we keep repeating, keep looping on this. If there's any vertex that can improve, you do it until you get stuck. Suppose the algorithm terminated. There's two options. Either now there's zero disputes. Everyone is now, the local views are in complete harmony. In this case, we're happy. And the second case is that there is still some disharmony. So let's see how to analyze this. First, we notice that the number of steps is at most phi, because every time a vertex changes its local view, phi decreases by at least 1. So already we know that the number of steps the algorithm takes is proportional to the fraction of bad local views. Maybe I neglected to say it, but the fraction of disputing pairs is also proportional to the fraction of bad local views. The reason is that if you have an edge in both G and G prime are an accepting local view, meaning G already sees kind of harmonious picture and G prime similarly, then they must agree. So when you start the algorithm, whenever there's a disputing edge, you know that one of the endpoints must have had an imperfect local view. Okay, so we know that the number of steps is small, assuming the rejection was small to begin with. Next, if you reach 0 disputes at the end, then you know that from this set of local views, you can define a perfect f prime, and you can bound the distance of f to f prime by the fraction of rejecting local views. That's not so hard to see. If you want to think about it, there's two kinds of reasons why f will differ from f prime. Firstly, if in the beginning a local view at G was imperfect, then on these squares, f might differ from f prime on the squares touching G. And secondly, if at some point during the loop, G changed its value from what it was to some other value, then possibly again, f prime will differ from f. So if you take account of all of these, you're still bounding the number of bits that you changed by something, a constant times the rejection probability. The most important step is to show that if the number of disputed edges at the end is not zero, it's positive, then it must actually be large. Constant fraction of the edges must be unhappy. And since the algorithm only decreased the number of disputed edges, it means that a priori when we started, we were already at a very disputed situation where all the local views were barely consistent with each other. And we already said that in that case, this inequality is trivially correct because the rejection is already a constant. And so definitely it upper bounds a constant times the distance because the distance is at most 1. Okay, so the main thing really, the heart of the proof is to show that if you end up stuck at a positive phi, meaning there is some dispute, then actually there must be a lot of dispute. So let's say something about that. Okay, so we want to show that if the algorithm gets stuck, then in fact it must be that the rejection is large. I wrote here 0.1, but this is just a fake number. Okay, so firstly, we look at this situation. Suppose you have two neighbors, G and G prime, and they are in dispute, meaning that the local view at G is some little tensor word, the local view at G prime is some little tensor word, but they disagree. Now, these two little tensor words share all these squares depicted here. And this, you can think of it as a column in the local matrix of G, and it's also a column at the local matrix of G prime. So they disagree on this column. Now notice that this column is actually a code word, right? So if G has some code word, G prime has some code word, and it's not the same code word, because of the distance of the local code C sub B, many squares must be in disagreement. Okay, so we figure out that if you have, G and G prime disagreeing, then they must have many bits on which they say different values. Now, if G thinks that this square is a 0 and G prime thinks that this square is a 0, then what do these other vertices think? Well, this vertex might agree with G, and this vertex might agree with this one, but one of the three edges must be an edge of disagreement. Okay, so in this way, we managed to propagate a disputed edge between G and G prime to some dispute either between G and its neighbor or between G prime and its neighbor, or on this edge, which is a parallel edge to GG prime. So we have three kinds of options. Either the dispute moves to neighbors, or to neighbors on this side, or to parallel guys. And we're now in the position to try to propagate and to show that if you have a little bit of dispute, you have more dispute and more dispute. And just like we propagated the distance of the code, we want to propagate the rejection. But the problem is that here we can only conclude that if G disagrees with G prime, it must disagree with some other neighbors of G. But this kind of doesn't propagate because you're always stuck at G. You're kind of, all your dispute edges are clumped around the vertex G. Sorry. Okay, so now comes the point about locally having the tensor code itself be locally testable. So think of this situation. G is in dispute with many of its neighbors, but between the neighbors, everything is good. So they agree with each other a lot. If that is the case, if we look at the picture over here, we have the following situation. G disagrees with some of its neighbors. So the dots here are the A neighbors. The points here are the B neighbors. And in this square, we have the distance two neighbors, the ones corresponding to all the squares touching G. So suppose G disagrees with a non-negligible part of its neighbors, but suppose that these guys all agree with each other. What this means is that under a suitable assumption on our tensor code word is that whatever is written here is not so far from a valid tensor code word. If you have many rows and many columns that agree with each other, you can correct it to a nice matrix. This is really the property we called earlier robust local testability of tensor codes, and this is the property that we need. So now you have this nice matrix, but then G would have already changed its mind and moved to this matrix in the algorithm stage, right? So this means that this cannot be. It cannot be that all the neighbors of G or most of the neighbors of G agree, whereas most of the neighbors of G disagree with G. We kind of have the local testability rule this situation out. And now that we have this structure, we know that when G has many disagreeing neighbors, the neighbors themselves must also have many disagreements among them. And so we use this random walk that moves from edge, disputed edge, through a square to another edge. And the fact that this random walk is an expanding random walk to show that the dispute edge is large. So I'm not going into more details, just hope to give you some kind of taste of the fact that we have a random walk that doesn't walk from vertex through edge to vertex, but also from edge through square to edge. So this is like a two-dimensional random walk, and we need this random walk to converge quickly as well. Okay. Lastly, before I end, I want to tell you a little bit about how high-dimensional expansion is related to this construction. Using high-dimensional expanders and high-dimensional complexes instead of graphs for constructing locally testable code is an idea that has been circulating for a number of years, kind of a new direction of research to think about high-dimensional graphs and their expansion. And kind of the intriguing feature of high-dimensional expanders is that they exhibit local to global features. You can prove something locally in a neighborhood and somehow use expansion to show that it holds also globally. And this is something like what we've seen. You show that tensor codes are locally testable, and this implies that the entire square complex is locally testable. Now, this idea, you can trace it back to Garland, who used this local expansion in the links of certain simplicial complexes to show that the cohomology of these complexes with real coefficients vanishes. And more recently, it was shown to prove the topological overlapping, co-boundary expansion, convergence of random walks, and even for analysis of certain error-correcting code properties such as least decoding. So this local to global idea kind of already has some amount of traction. In a work that predates this one, we showed that locally testable codes can be analyzed on high-dimensional expanders, and if you find a way to construct them, then local testability will follow. Unfortunately, in that work, we didn't know how to construct the codes, and in fact, I still don't know how to do it on a simplicial complex, but we managed to move to these square complexes where this did turn to work. So this is kind of still an open question. Can you find good local codes on, say, these LSV Ramanujan complexes that come from quotients of the Brotitz building? Can you kind of instantiate it in a way that you get a locally testable code? Okay, so thank you. Let me mention two kind of big open questions. One is, locally testable codes originated from probabilistically checkable proofs. So it would be great if some of these techniques can be used to construct new PCPs, maybe simpler constructions, maybe better parameters. That's a kind of high-level open question. And a second thing is, local testability is quite practical in theory. Can it be practical in practice? So with this question, thank you very much for listening, and thanks for the invitation to speak in this series.